So now we want to know how can we extend a perceptron to multi-class classifications. I mean, we use the perceptron for binary classification problems, which is easy because the perceptron will have number of inputs. It could be x1, x2, x3, for example, and we have bias. Inputs are connected to our perceptron using some weights, and we have a binary classification. We have this unit step activation function. So, and we need to use an optimizer. This optimizer, it's an algorithm which will be used for adjusting the weight values and the bias values. So we can generate a decision line which can separate my two classes into two different classes. So we need to find the decision line. We need to find the parameters of the decision line. The parameter of the decision line will be omega 1. Or for example, if it is in two-dimensional space, it will be omega 1, omega 2, and the bias B. So now we need to know how can we extend this to multi-class classification. Is there any way to do it? So we need to still use a perceptron, but we want to extend it to multi-class classification. Multi-class classification, yeah, it's in many cases. For example, this iris dataset, we have three classes. We have three classes. So can we use a perceptron for classifying iris dataset? Iris dataset, it's three classes, so it's not a binary classification problem anymore. And we need to build a model for classifying it. So in this case, we will use a technique. And this technique, it's called one versus rest approach. One versus rest, and one versus rest approach. It's a common technique to extend binary classification algorithm to multi-class classification. And in this one versus rest approach, a binary model is learned for each class. We will build a model for each class, which will try to separate that class from all of the other classes. So we have three classes. We have 0, 1, and 2, for example. So we will build a model to classify class 0 from the rest. And after that, we will build a model to classify, to separate class number 1 from the rest, which is 0 and 2. And so on. We will do it for class number 2 also. We will try to find a decision line which will separate class number 2 from class 0 and 1. So the idea here, in fact, is to build a model to have one binary classifier per class. So we need to have one binary classifier per class, and of course each binary classifier will have its own coefficient omega and bias, right? So we will build three models. So if you have three classes, we will have three perceptrons. If you have 4, 5 classes, you will have 5 perceptrons, and so on. So indeed, we will have a model. We will have a binary classifier for each class, but it will deal with the data as follows. It will try to separate one class from the rest. So one class will be, for example, class 1, and the rest will be zeros. And in this case, we will build a model, and we will repeat this process for each class. So finally, at the end, we will have n number of perceptrons for n number of classes. sklearn provide some sample. I mean, we can work with iris directly, but I prefer here to start with a data set which is generated by sklearn. sklearn provides sample dataset generator to help you to create fast and easy to use custom datasets. We can generate some toy datasets or customized datasets. Those datasets are useful because we can use those datasets for testing different algorithms, and discover how those algorithms works and so on. So it will be much easier because it's customized. So we know the distribution of the dataset. For example, we can control values, number of classes, amount of overlap between classes, and so on. So we can really generate very customized dataset for testing our models. So this is an example. For example, we have a function called makeplups. Makeplups, it's from sklearn.datasets, and this one, it will just generate plups. You can decide. By default, it generates three classes, and you can decide also the sample size. You can decide noise, for example, how much noise in the dataset, and the amount of noise will control the amount of overlap between different classes. make blobs data set. I mean, we need to build a logistic regression model. We need to build a logistic regression model for this data set. So I mean, we will generate 3 classes using make blobs. So make blobs data set, it's a data set which is already provided in sklearn. So we will use this function for generating 3 classes. We will have this blue class, we will have the green class, we will have the red class. So we have 3 classes. It's similar to Iris dataset. But here we have 2 features, right? We have 2 features, and it's 2 features because it's easy to visualize it in 2-dimensional space, and it's easy to plot your decision line. And the idea here, we need to use one versus rest approach for building a logistic regression model to classify those 3 sets or 3 classes. So we need, I mean, we need to generate 3 decision lines. And as we mentioned before, I mean, one versus rest means, for example, if I need to build a model for this red class, right? So how can we? So we will deal with this one as class, for example, number 1, and the rest will be zeros. This one will be 0, this one will be 0. And in this case, we will use a perceptron for classifying this new data set, right? So we combine the other classes into one, and we will try to generate a decision line which will separate class number 1 or the red class from the rest. So we can get this line. So we will have this line. This line has some parameters, the parameters of, because we are in 2-dimensional space. So this line will have, for example, its omega 1 and omega 2 and bias. So each model will have its own parameters. Do we have any questions? Yeah. So we will generate this line, and this line, as you can see, it will one versus rest, because it will separate the red class from the rest. And we will repeat this one for each. We will repeat this process for, I don't know if we have some colors here. Yes. So for example, we will do the same for the blue one. So for the blue one also, we will call it, for example, class 1, and the rest will be class 0, and we will try to find a line which will separate this class from the rest. So maybe we can draw a line like this one, right? So we will draw a line like this one. This line also, it has its own parameters. So it has its omega 1 and omega 2 and bias, because it's a straight line, and it's parametric line, and it has its own parameters, omega 1, omega 2, and b. So now we have the second perceptron. So one perceptron will generate a red line, and one perceptron will generate the blue line. We will do the same also. This time for the green set. I mean, we have this green class here, right? So we need to generate also a perceptron for classifying this one. So we will deal with the green class as a class and the rest as another class, right? So it's one versus the rest. And from this one, we will use a perceptron, and this perceptron will help us to generate a line like this one. So now we have 3 lines. This line also, it will have its own parameters, omega 1, omega 2, and bias. So now we have 3 lines, and each line, it has been generated by a perceptron. So we should expect that we will have 3 perceptrons. So in fact, if we need to, so Magnus, do you have any question?
Yeah, I'm just wondering, you have 2 plots there, one which you've drawn on and one which the computer's drawn on. And in the one where the computer's drawn, the 3 decision lines all intersect at the same point, while in yours there's a space in the middle. I'm wondering, is one superior to the other?
Yes, because in this one, which has been drawn by the computer, we have the red, for example, the green one, for example. So this is a green line, you see it? So the green light, in fact, it will separate the green cluster from the blue one and the red one, right? So this is a decision line for the green one versus the rest. So the one here, it will be the green class, and the rest will be the blue and red.
Yeah, sure. That's not what I mean. What I mean is that in the one where you've drawn, the one where you've drawn, you have essentially 4 regions. You have the green region, the red region, the blue region, and the nothing region.
In the middle here.
In the middle, yeah. Is there is it beneficial in some way to have that nothing region in the middle, or would you rather have it intersect like in the plot on the right?
In fact, I don't know. We need to run this one for maybe more number of epochs, for example, or less number of epochs, and see if it is by intention. I don't know if it is. It should be intersect in the middle or not. In fact, right? So because yeah, so you want to say that maybe they use it with and or. So the green one and ending and oring those decision lines, we can make decisions that this one belong to this one or that one, right? So I mean, for me, we will have a decision line. So all points above it, it will be positive, right? And the rest will be negative. So if you can if you can make it as a vector, for example. So if we have vectors, so imagine that I have a point here from the green one. So for this decision line, it will be positive, and this one and this one, it will be negative, right? For the green one, for the blue one, for example. So for the blue one, this one will be positive, this one will be positive, this one will be negative, right? So I don't know if they are oring and ending it at the end or not. So I don't know. In fact, I'm not sure if this one is if we will have nowhere, for example, in the middle or not. Because we will put some restrictions. So if we want the three decision line to intersect in the same point, maybe it's too much. It will take too much time for calculations. We will lose some degrees of freedom. I have no idea. In fact, we need to test it. But so maybe we need to test it with another data set. For example, we will test it here today with Iris data set, and we will plot the three decision lines, and we will see. So if I can go here. So first, I mean, we will have the three decision lines here. For class number 0, we will have omega 1, omega 2, and under the bias. For class number 1, we will have those omega 1 and omega 2 and the bias for class number 2. So those are the parameters of the three decision lines. I did it for Iris, but in fact, so I used a perceptron for Iris dataset. So I mean, if we can extend the line, because maybe this is one line, it's just plotting the regions. So this is the region, in fact, for class for each class. So maybe you are right. Maybe they are intersecting in one point, right? So I mean, if we can extend those lines, right? Do you see here? So maybe they are intersecting in one point. So maybe you are correct. They are intersecting in one point. And finally, using some logic, they will decide that, I mean, points which are located between this line and this line, it will be one class. Between this one and this one, it will be another class. Because it's just, this is a decision line for Iris dataset. So yes, I guess the three lines are intersecting in one point. Yes. Yes, Magnus. So I guess the three lines should intersect in one point. Maybe it will make it easy for making decisions. Maybe this one, it's so maybe the three lines must be intersect in one point here, so we can avoid this region in the middle, and it will be easy for us to make decisions. So maybe all points which are located between, maybe this one will be one class, for example, right? Maybe this one will be another class. Maybe this one will be a third class, right? So if you want to implement it, you can just go to this code. It's perceptron for multi-class classification. Perceptron for multi-class classification, and at the beginning here, we need to import make plups. So we have this function, it's make plups. We got it from sklearn.databases, datasets, and to generate it, it's just xy equal make plups. And by default, I guess it will generate 100 points. So you need to check, I mean, the inputs to this function. So because I know that you can decide how many classes. I mean, you can decide here. I mean, by default, it's 3 classes and it's 100 data points. But you can check. I mean, make blobs, and I know that we can generate any customized data set. So you can specify here the amount of noise, for example, and you can decide the noise and the number of classes and number of data points. Yes. Yes, someone was knocking the door. So now you can generate. You need to generate. I mean, your data set, right? And just plotting it. We will have two features here, and we have 3 classes: class number 0, class number 1, class number 2. And just upload your data set, and after that, build your model. So model equal logistic regression, fit the data. I mean, fit the model in your data, and predict. Print model coefficient. In this case, the model will look like this one because we try to extend it into multi classification. So we have 3 classes, right? So the model will be like this one. So we will have 1 perceptron for each class, and we have 2 inputs, in fact. So we have 2 inputs. We have x2 and x1. We will connect those to each model, and maybe I can change color. So the second input, it's connected also. So we will have 1 perceptron for each class. So this one will be class number 1. I can just call it y1, for example, y2, and y3. And of course, each model has its own bias values. So we will have here also, I mean, bias value. So in fact, each model, each perceptron, this one has omega. I can call it omega 1, this one it's omega 2, 1. This one it's P1, right? This one it will be, for example, it's omega 1, 2, omega 1, 3. This one it's omega 2, 3, and omega 2, 1, 2, 2, for example. So we will have is the coefficient. It should be a matrix. So omega, it should be like a matrix. This matrix, it should be 2 times 3, and the bias will be a vector, and this vector will consist of, it will be 1 times 3, for example, a vector, right? So 3 values. So now we can have a model. We can have a perceptron for each class, and we can just draw the decision lines as we did before. But in this case, you will put it in a for loop because we have 3 decision lines. So after training your model, now you have your model coefficient, model and intercept, weights and intercept. You can just plot it as we did before. So it's a decision line. We need, for each decision line, we need to generate x1. I mean, the graph will be like this one. So the features, it's x1 and x2. So I will just generate some values for x1, right? And using those values, I will substitute it into this equation to get values for x2, right? I mean, and the decision line for each model, it will be just the same. It will be omega 1 x1 plus omega 2 x2 plus b equal 0. If you know x1, we should be able to get x2, right? So if we know x1, because we will generate values for x1, so in this case, I will substitute those values into this equation to get x2. So x2 will be negative omega 1 x1 plus b divided by omega 2. It will be like this one. So this is the equation. So it will be coefficient omega 1 multiplied by x plus the intercept divided by omega 2. In this case, we can generate x2 and just plotting it. And when we plot it, we will get the decision lines, which we have here. Yes. So now, if you can go to this code, this make BLOPS logistic regression. Make BLOPS logistic regression. Try to run it, please, and after that we will extend this one. We will use this one for Iris dataset. We will use this one for Iris dataset. So please just run. Try to go to this code, this example, and just feel free to change and make some changes, for example, and try to run it. And after that, we will go for Iris dataset. So now please go to the code. I can open also this one make BLOPS here in my computer. So I want to find so it will be I have perceptron for multi-class classification. I don't know. No, it's make BLOPS.
The link is in the chat.
Okay, but I need. Oh, yeah, I'm just opening it from here. So it's make BLOPS logistic regression. So I'm opening it here. Just make it small. So okay. So now I used this make BLOPS. I imported it from sklearn.datasets. I will run all, right? But you can make some changes here. So if you want, for example, to work with four classes, you can just generate 4 classes. By default, we get 3 classes. And I guess by default, we get 100 data points. Yes, it's 100 data points, and it's 3 classes by default, but you can generate your custom data set. You can, for example, add noise. For example, when you add the noise, you will get some overlap between different classes. Do you see? It's easy. This data set, it's just very easy because we have long distance between classes, but we just used it for testing this. For model building, I used the logistic regression, and the logistic regression, it's from sklearn linear model. It's called regression, but in fact we use it for classification. And I just fit the data into the model X and Y. I didn't divide my data set into training and testing, but you need to do it. So when you are working with a project, you need to divide your data set into training and testing. You need also to decide if you will go for holdout, validations or cross validations. So it's according to the amount of data. This is the model coefficient. So now I have omega 1, omega 2, omega for each perceptron. So this one, in fact, each row, it's for each perceptron, and each column is for each column of features for each feature. So this one, feature 1, feature 2. This one for perceptron 1, perceptron 2, perceptron 3. And if you want to plot it, I just plot my data points here, and I generated some values for x1 from -10 to 10, and plotting my decision line. So we can make some changes. For example, we can try it for four classes, right? But we need to make some changes here. So, or for example, increase. You can just make BLOPS. So make BLOPS, it has lots of, some parameters here which we can use for making it more complex. So for example, number of samples, centers, number of features. So you can do a lot, in fact. You can do a lot. Maybe centers, it's the number of classes, for example, and also noise. So you can just play with it, for example. You can try it for, 4 classes instead of, maybe you can try for before, for example. So we have 4, but we didn't plot it. So in this case, we will have the class number 3, for example. So it will be maybe this one, it's a 3. It's blue, green, red, blue. I don't know, maybe magenta, for example. It should be diamond. We call it class number 3. For example, we can just, we can try to make it complex and play with it. So now we have 4 classes. Maybe this one, it's upper left, it should be maybe upper. So now it's a more complex. We have 4 classes, right? And it's 25 from each class. For example, you can, I mean, as I told you, by default, number of data points generated are 100. You can generate more. Now we can. I mean, we got different model. I just need to copy this line here. Plotting. So in fact, I mean, maybe this assumption that the 3 lines must intersect with each other, but I don't know what is the accuracy in fact here now. What is the accuracy? So if we look into the blue line, do you see the blue cluster here, blue class? I mean, this one, it's for this one, in fact, right? So so the blue line here, we will use this blue line to separate this class from the rest. The red one will be used for separating this one from the rest. Magenta, it will separate this one from the rest. Green one, it will separate this one from the rest. But those lines are not good enough. Maybe we need to increase number of, it might need more time to train, right? So in logistic regression, maybe we need to add more number of epochs, because number of iterations, maybe it's not enough, right? So so logistic regression is key. So here, I mean, we can define many things here. In fact, I mean, the solver, what type? I mean, maybe we need to select some different types of solver, for example. So I have an example here. Maybe we can borrow some from it. Yes. Is it? So now it's more complex, right? And we need to train our model more. It needs more time for training, right? So just try to make some changes, and no, we don't have this one here. Should not have this one here. LP sync. Okay. So just need to, I mean, we need to play with those numbers. Okay, I want it to train more, right? So I can just, I don't know if it called the maximum iterations or not. Okay. No, we have still here some error here, right? I mean, so one versus rest, it's not maybe working optimally here, but we need to optimize. We need to work a little bit with those numbers and. So you can just try to play with those numbers and try to. I don't know if you can see any improvement. Can you see any improvement? Maybe, I mean, maybe it's impossible to get because those sets are very close to each other. And you see? So it's hard to find a line here to. So for the green class here, it's impossible because, I mean, one versus the rest. For the green one, it's hard because maybe it could be something like this one, but we will have this one wrongly classified. So we just need to find accuracy. So if you can check the accuracy of this model, it would be great. I don't know, model.score, is it working here? Y, it's Y. This one is not working here, model score. Can you check, please? So why this one is not working here? X and Y. Okay. Okay, it uses X and Y. Yes. Maybe just. So. So it's just one. What does this mean? It means that accuracy is 100%. So I mean, as a conclusion here, it's not important that maybe the lines intersect with each other in the middle. Maybe by chance, I mean, in this problem here, it was, I mean, easy. But also, if we go back again to the three classes, we can go back to the three classes and increase maybe the noise. So you can go back here to the random one, but noise, we need to add some noise. So you can have some overlap, for example. You can get some overlap. Noise, no, I don't know. So it's a cluster standard deviation shuffle random state. So it does not have any noise, I guess. So yes, so we just need to play with around this function and try to make it more challenging for your classifier. I don't know if yes, so maybe it could be like so now we can make it more difficult, and we can just do it for
Ibrahim?
yeah. Yes.
Hello?
Yeah, hello?
I got better lines if you define the multi-class.
Okay, can you share it with me, please? Can you share your
Yeah,
screen
I can try.
for four clusters?
For 4 clusters,
Mhm.
you have disabled screen sharing.
Okay.
Oh.
You have a vacuum cleaner?
One more.
Magnus, you are.
Yes.
I mean, who should I share the screen with?
Stefan,
Stefan. Okay.
if you share with Stefan, I will try to show you.
But I want to allow all people to share screen, in fact. So how can we do it? Okay, Stefan. But it's strange. So I make you a host or a co-host, for example. So now can you share your screen?
Yes, but this will stop your screen sharing.
No, yeah, because you can just return back me as a host, but I'm still a host.
So can you see it now?
Yes.
So I have put the 4 centers, and you can't see it because of the layover of the class, but there's a blob behind this. And if you go here and you say multi-class OVR in the logistic regression, and now I'm running 10,000 iterations, but
okay, so we need to have this option multi-class.
Yeah, and then you will get these lines. So you see they're separated. So this dashed line is separating the one blob, and then the green line is separating all the others. Yeah, like
So
I
they
would
are
have
not
drawn it if I was doing it manually.
okay. And this option is called the multi-class, called
multi-class, and then there's different options. But since we're working with the OVR, I was using that.
Okay, very good. So this is
Okay,
very good. I thought that we can do it without having this option. So I will go back to my. Can you give me a screen so I can?
I will try my best. There we go.
Okay, thank you very much. So I will do it again here in my file. So okay, so we will have 3 classes again. Okay, we can just make it 4 classes, and standard deviation we can just make it 1.5. So in the model here we just need to select multi-class. Okay, this is very good. Oh, this is very good. So I mean the idea. So because of the question today from I guess Magnus, he was asking if those lines must intersect in one point. So maybe it's not. I mean, not very important, right? Maybe it's by chance. So for this model, we have. I mean, we have 4 classes now, and we have those parameters of the lines, and we can plot the decision lines. If you can also, Stefan, if you can also check, I mean the error prediction error, it would be great also. So this one, it's model score. It's 1, which means 100%. So we need to double check. We need to double check this one. But okay. So multi-class. I mean multi-class classification problem. It's very important, and so I don't know also if we will just make it less number of epochs, what will happen? Yeah, I mean we have some errors here. Increase number of iterations. Okay, so it's asked us to increase the number of iterations. So okay, so I guess we can go forward with that part. So I will share my my slides one more time. So now it's not important that we have intersection here in the middle, right? So it could be, I mean, we tested it was 4 classes, and it's hard, of course, to get those 4 lines intersect. So it's according to the distribution of your data. Yes. So we, I mean, we know how to do it, how to plot. So now we need to repeat this one for Iris dataset. So the task now is to do it for Iris dataset. So in Iris dataset, we have 3 classes. The first 50 points are, I mean, related to one class. So we can just, I mean, Setosta, it's a 0. This one, it's a 0 class. This one, it's 1. And this one, it's 2. So we have 3 classes. So can you just repeat this problem again for, you have the code already for this make PLAPS, for the PLAPS. So just repeat it for Iris dataset. And we need to see how the response will look like. You can just have, for example, 10 minutes or 5 minutes for Iris dataset. So we will stop now, and we will start again after at 12 exactly. So we have 8 minutes to solve Iris dataset. So we will meet after the break, after 8 minutes with the Iris dataset.